Okay, so we are going to do measures of spread. Get to that later. Well, when we did measures of center, we found the center of what? Data. Right. So now we want to find the variation in data. So I'm going to take 3 cases. Okay, so we have 3 different samples. So there's one, 5, 8. What is the mode of that? Good. So, what is the variation in that sample? There is no variation. It's a constant 8. It's just 8, no variation at all. So. We can let that be. The second and the third, observe them and let me know which one has greater variation. The third one, why?
Because the difference in the intervals are like standard deviation.
Also, it goes up and then down.
Yeah.
Goes up and then down. This has greater variation. Because you have some values that are like 12, 16, and all of a sudden there is 112. So there is a lot of spread, and that's why we call it a measure of spread. So the simplest one that we have, you are going to sum. So let's say the average is 5. The bunch of points between 2 and 8, the average is 5, 2.6 is the minimum, 7.4 is the maximum. Would you consider that this particular data set has a lot of variation?
No.
No. How did you know?
The values are closer together.
The values are closer together. Okay. What else?
No outlier.
No outliers. Okay. Values are closer together. What is another way of looking at it?
The domain is not large.
The domain is not large. And what is the domain here?
There. 2.6 to 7.
2.6 to 7.4. But domain is not, I know what he's trying to say, I guess it, but it's not the domain. But the minimum value and the maximum value are right here. So if I want to measure the spread between 2.6 and 7.4, how would I do it?
Measures of variation.
Great. Which one? So I have agreed with everything that you guys said. So they're all close together, so not a lot of variation. And you said, okay, the domain is 2.67.4. It's not actually the domain, but the observations are between 2.6 and 7.4, including those 2 points. And if I ask you, well, quantify the spread for me, how far they are spread apart.
7.4 minus 2.6.
Okay, thank you. So 7.4 minus 2.6, the maximum minus minimum. And that is what we call the range. Do you believe that range is a good measure of spread? Hunter says no. Enthusiastically, why?
I feel like it's just very, I don't know, I think it's like a very simple way of doing it, and it doesn't accurately calculate it.
Okay, so you say that simple things are not good.
I'm not saying always, I'm saying,
What else?
I may be wrong, but I actually do think that it's good measure of variation. You're taking the largest value and you're making that your time for outliers, including when you do the smallest value.
So is that a good thing or a bad thing?
No, that's a good thing when you want to measure variation.
So, oh, I see. Do you
I
have-
was just gonna say, sure, you have bias outliers.
Exactly. If we had outliers, we will have bias. It's not a good thing. Suppose you had majority of the observations here, 2.6 to 7.4, and arbitrarily you've got one at 174. You're going to call the range to be from 2.6 to 174. But in reality, the actual range, actual variation, that matters is right here. Does that make sense? So range is not a good measure. So what is? I have to erase that. Variance is a good measure of variation. So there are two different types. One is sample, the other is population. Notationally, population variance is denoted by sigma squared. I call it drunken six. Six got drunk and fell down. So sigma squared and S squared. As far as this class is concerned, we are going to stick with sample variance. This might pop up here and there. Now, what is the difference between the two? I will explain the formula once I get to the picture here. Good enough to get the point across. So let's just say that the average is 8. Now, we know that if I took the maximum value, subtracted the minimum value, I would get the variation, a measure of variation, but that's not a good measure. So what we would do instead is to look at the average and say, well, where does or how far does each point lie relative to the average? So you measure the distance between the average, which is x bar. I'll just call this x1, x2, x3, x4. I'll call that x5 and x6, put it backwards. So from the center, which is the average, I'm going to find the distance here, there, and there. Same on the other side, do it with every single observation. And if I took the average of all those distances, then I'm going to get a good measure of that variation. But the problem is, these lengths are called deviations from the mean. And when you simply sum them, you will end up getting 0. The reason being, whatever you computed here about the mean will negate whatever that's below the mean. So you end up calling this to have no variation whatsoever. So to avoid that, we rather take the square. If I square the observations, then I would simply have positives everywhere and take the average of the squared values, squared deviations, I'll get a sample variance. So this is the formula. So I'm just putting it up here so that you don't get spooked when you see something like this in the homework. But this is working hard. We're going to work smart using the calculator. So the goal is to find the distance x1, all the x1 minus x bar, x2 minus x bar, square them all, sum them all, divide by n minus 1. In other words, we are finding the average of squared deviations. You may ask me, well, shouldn't you divide by n? Well, that formula comes here. Mu is the population mean. So there is a reason for this. I'm not going to get into it way beyond the scope of this class, but sample variance here will have n minus 1. Population variance will have n. The calculator is going to give you both. I'll show you how to find them. So if, my lab says, do it manually, I'll do it manually, right? If you have 10, 20 observations, do you really want to sit there and do it manually? We don't have time for that. So use the calculator. Are we good? So that is the formula for variance, but we're going to use the calculator. If you take the square root of variance, you will get the standard deviation, and by all means, this is a proper measure that is going to give us the variation between observations. Okay, so we entered the data, and I am thinking that there isn't a lot of deviation. So how did we find the mean?
Count 1.
Count 1.
Yeah. Stack.
Start,
Count,
count,
1 bar stats.
1 last start. Okay. And second one. The first line, of course, is the mean. And the fourth one, Sx, is the sample standard deviation. That's value right there. Sigma x is the population standard deviation, which is the square root of population variance. So we have the value of S for that problem, 1.537, and the value of sigma is 1.4658. As far as this class is concerned, we're going to use S more than sigma.
So we're not going to be really asked to find sigma.
My math might ask.
It might.
Yes,
Okay.
probably.
But not
Put on a test or not.
haven't written the test yet, so just understand the difference. Would I put it there personally? I don't think sigma is important in this one.
Okay.
So the chances that I would put it slip. Okay, are we clear with S and sigma? So S is the sample standard deviation, sigma is the population standard deviation. So how do I find variance if I know this value? Compare them.
Yes.
So S is 1.537. I like to find sample variance.
Where is
I would square 1.537. I would end up getting the sample variance. Does that make sense? Yeah. Yes. So don't, do it manually. It's going to take forever. But if you want to know more about the formula, you are more than welcome to come and talk to me. So Stebyshev's theorem, it's useful because we're going to talk about something called the empirical rule. You can verify the rule if you understand the theorem. So what did this guy say? Well, if k is not equal to 1 and greater than 0, in other words, has to be bigger than 1, simply put. Obviously, k cannot be 1 because if k is 1, then 1 over 1 squared is 1 minus 1 will be 0. That doesn't make any sense. So if k is not equal to 1, then the theorem that he proved was at least 1 minus 1 over k squared percent of the observations will lie within k standard deviations from the mean. So x bar is the mean. S is the standard deviation. So k times s would simply mean k standard deviations. So we're not subtracting k or adding k, we are adding k standard deviations and subtracting k standard deviations. So his argument was, well, if this is the case, of all the observations in the sample, at least 1 minus 1 over k squared percent will lie here. The key word here is at least. He's not saying that it is exactly going to be 1 minus 1 over k squared times 100%. He's just saying at least. So this amount or higher will lie between those two values. Does that make sense?
Why KS?
Huh?
Why KS?
K standard deviations, K multiplied by S. Good? When I do a problem, it makes sense.